All right, welcome back. We are in section 4.1 on area and distance. Area and distance. And last time we approximated the area underneath this curve, underneath the function f of x is equal to x squared. And we considered the area on the interval or 0 to 8 underneath the curve between that and the x-axis, and we call that region S. And last time we approximated it with 2 intervals. This time we are going to approximate it with 8 intervals. So let's do that. I am going to split this up into 8 rectangles. Oop, that one doesn't look very good. There we go. And let's first of all start by figuring out what's the base of each rectangle. The base of each rectangle, well, I'm taking the distance from 0 to 8, which is 8 minus 0, and I'm dividing that into 8 pieces because I have 8 rectangles. So that's 8 over 8, which gives me 1. Each rectangle has a length of 1. So I'm dividing the interval from 0 to 8 into 8 subintervals, from 0 to 1, from 1 to 2, from 2 to 3, and then they go all the way to from 7 to 8. So there's my first step. I need to know the base of a rectangle in order to find the area. Next step is I need to figure out the heights. And I'm going to start by, first of all, deciding, do I want to use the right endpoints to the left endpoints of each interval. I'm going to use the right endpoints for this first one. So that will be the picture of the area that I am finding. Okay. So I have 4 rectangles that I want to find the area of. Let's see the heights. The height of each rectangle is, well, just like we did previously. This is the point 864. I can find the height of that rectangle by taking the function value and evaluating it, or the function itself, and evaluating it at this right endpoint. I'm just going to write that in general. The height of each rectangle is f of the right endpoint. The right endpoint. Okay, so I'm going to call this area R8 that I'm finding. So this is the estimated area using 8 rectangles. 8 rectangles and the right endpoints and points of each of those intervals that I'm using to divide up the interval from 0 to 8. That R8 area is equal to, well, it's equal to, let's say, the base of rectangle 1 times the height of rectangle 1, which is f of 1, that leftmost endpoint, plus the base of rectangle 1, which is 1, times the height of rectangle 1, or rectangle 2, which is f of 2. That is the rightmost endpoint of the second interval. I can see a pattern here. Plus 1 times f of that leftmost, or that rightmost endpoint of the third interval here. And the others will continue in that same pattern. Plus 1 times f of 4 plus 1 times f of 5 And then plus 1 times f of 6. We have 6 rectangles so far. Plus 1 times f of 7. That's the 7th rectangle. And then plus 1 times f of 8. It's the 8th rectangle. I need to find what f of 1, f of 2, f of 3, etc. are. 1 times f of 1 is 1, plus 1 times f of 2 is 4, plus 1 times 9, plus 1 times 16, plus 1 times 25, plus 1 times 36, plus 1 times 49, plus 1 times 64. So if I add all of those together, I get the right sum, which is 204. I was using the right endpoints of this. All right, let's do the same thing, except let's use the left endpoints of each interval. Okay, so I'm going to draw my figure again. This is the area that I am concerned with right here. This is the point 864. So I'm wanting to estimate that area. I'm going to again divide it into 8 pieces. There we go. And the intervals that I'm concerned with are the same. 0 to 1, 1 to 2, and so on till we get to the interval 7 to 8, where this is 8. Okay, so this is 1, 2, 3, etc. This is 0. All right, the base of each rectangle is the same. It's still 1. The heights, well, I'm using the left endpoint. So my leftmost rectangle is going to look like that. Next one is going to look like that rectangle, and so on. So that is the area of the region that I'm wanting to find. Those are the 8 rectangles that I'm estimating the area S with. The height of each rectangle is, well, I'm using it by calculating the function value at the left endpoints. The left endpoints. So the height of each rectangle, I can calculate using the left endpoint of this interval for the first rectangle, left endpoint of this interval for the second rectangle, etc. So that means L8, the area of those rectangles in total, is equal to the base times the height of the first one, which is f of 0. 0 is the leftmost endpoint here, plus the base of 1 times f of 1, plus, we continue on pattern, plus 1 times, let's see, our final interval is 7, 8. So I need f of 7 as the height of my rightmost rectangle. So I need to find what f of 0, f of 1, etc. are. This is 1 times f of 0 is 0, plus 1 times f of 1 is 1, plus 1 times f of 2 is 4, 2 squared, plus 1 times 9, plus 1 times 6, plus 1 times 25, plus 1 times 36, plus 1 times 49. And so that is multiplying the base and the height of 1, 2, 3, 4, 5, 6, 7, 8 rectangles. If I add those all together, I get 140. Okay, so this is the left sum. And I can again tell that it is an underestimate. It is an underestimate, or I could call it the lower estimate. Lower estimate, or lower sum if you prefer. And I can tell that the actual area underneath that curve is greater than 140, which is the left sum with 8 rectangles. It is also less than 204, which is the upper sum. It is the overestimate that we got using the right endpoints of the rectangles. Okay? But this is a much better approximation than the previous one that we had. You might recall previously when we used 4 rectangles, we got values in between 112 and 240. So it looks like we have narrowed the range of the area by quite a bit. I know that I can guarantee that instead of the area being just between 112 and 240 square units, it's between 140 and 204 square units. So that narrows down what the actual area is. Now, we could keep going with this process. We could keep dividing this area underneath the curve into smaller and smaller areas. In other words, rectangles that have a narrower and narrower base, which means that we would have more and more rectangles. And the more rectangles we use, it turns out the better our approximation of the area is. Let me go ahead and write that in formal way, well, informal actually, but we can observe that the more rectangles we use, the better the approximation of the actual area A. The approximation of the area A. Now, the actual area is 170 2/3. I might be able to express that area as perhaps a limit of a certain quantity. Notice that as the number of rectangles gets larger and larger, so as n approaches infinity, as the width of each rectangle gets smaller and smaller, the estimate of the area gets closer and closer to the actual area. So as n approaches infinity, where n is the number of rectangles, n is the number of rectangles, the Rn, which is the right endpoint sum, gets closer and closer to A, which is the actual area. I could write that in limit notation as the limit as n approaches infinity of Rn is equal to the exact area A, which in this case is 170 2/3. It turns out the same thing happens with the left sum. the limit as n approaches infinity of ln is equal to 170 and 2/3 in this particular case. I kind of want to be able to prove that. Let's show this. We can see pictorially how it happens, but how could I actually get that number 170 and 2/3? That's what we're going to do in the next video.